Welcome everyone, depending on your time zone. Good morning, good afternoon, and good evening. This is Remoticon 2020. My name is Bruce Dominguez. I'm here as your kind of MC moderator for our event. And today we'll be talking with Alex Whitmore. And Alex is an electronic and prototype engineer who specializes in turning napkin sketches into proof of concepts with a path to production. So welcome everyone to the basics of RF emissions debugging with Alex Whitmore.
Thank you much. So, yeah, we're basically here to figure out what you do about fixing a product that failed an RF emissions test. And we'll start from the beginning and dive right in. Let me figure out how to share just my one window. There we go. All right. So first things first, these slides are available as a public link right now. And I kind of suggest that you go find that link and download them and follow along from home, because there are a bunch of live links throughout the slides. And I think everyone's path in this is going to be slightly different as you follow along and realize some software doesn't work for you or there's some problem or whatever. And I'm trying to allow for a whole bunch of time for like live debugging of this. I believe that link is already in chat. So like scroll up to the top and see if you can find it.
I'll repost it because sometimes I think that once you enter in at a certain point, it doesn't log in.
Yeah. If it was before then, yeah, I got it.
Yeah, I just reposted it.
Okay, cool. Yeah, so background, first slide has a link to the setup instructions that I tried to post some instructions weeks ago. I know some people have been following along. I kind of don't expect that everyone will have. So we're gonna have to like catch up as we go, and I'll try to circle back around. Keep the chat lively with problems that anyone is having so that everyone can flag me down and turn me back around if some help needs to be pointed out or there are issues that everyone's having that I haven't or something like that. In particular, what we'll need to set up before we get started is obviously physical materials on your workbench, an SDR toolchain, and the toolchain for programming a tiny FPGA. The instructions, like I said, are up for that. And in a perfect world, the best way to go about doing that is to just like download the pre-made virtual machine that I've got, but we'll get there anyway. So first things first, what do you actually need on your workbench? It should look kind of sort of something like this. I told everyone to grab the NESDR Smarty just because it has a built-in bias tee for powering the low noise amplifier. I also pointed out you don't need these per se, but you do need an RTL SDR that you can run and a low noise amplifier that you know how to turn on. And then I have some probes that I've already made. And of course, a tiny FPGA BX for demo purposes, demo signal purposes. You definitely don't need this RSA that luckily a client rented for me. So we'll be able to have a look at what you would be doing if you had money to spend. And then above and beyond that, since I imagine a lot of you will be building probes live as we go through the workshop, it would probably be a good idea to have a soldering iron handy and your magnet wire and SMA connectors if you haven't already built probes. And ideally some other boards to probe around as well. Like you see the Alcatree AU over here that I've got some interesting investigations to show on that. And like, I'm sure an Arduino will probably work. There are probably countless boards that might do the trick. The long and short of it is we're limited in what we can see by the SDR because it bottoms out at 25 megahertz and we need a signal higher than that in order to see it at all. That's really the only issue here. But yeah, bring along your own boards and we'll have a look at them later because there are certainly a lot of interesting things to be seen on your own. There we go. So first things first, software setup. The tools that I plan on using in this workshop primarily are Q Spectrum Analyzer. Obviously, I'll walk through all this stuff, but That basically approximates a traditional swept spectrum analyzer using any of a handful of SDR devices, and in particular our RTL SDR. So that's super useful here. And then SDR Angel is the best general purpose SDR tool that I've come across for taking a spectrum, because it offers a lot of like fake digital phosphor features, which we'll get into why that looks pretty, and it'll be pretty obvious as soon as we dive in. That's the best one. Generally speaking, if you can get any spectrum with your SDR at all, you're in good shape. So like even if you're using GQRX or like something like that, if you can see a spectrogram, you can follow along. If you can't, then that's a little bit of a problem. I recommend everyone download this VirtualBox VM that I put together with Dragon OS LTS. Setting up all of these tools is kind of the worst, and it's very platform and system dependent, whether it works or whether it goes smoothly or whether it doesn't at all. This VM I know works in VirtualBox, at least on my machine. The performance is not that great, so if you're on Windows, I recommend you try to install the VMware Workstation and import the virtual machine into that and run it that way. If you're on Mac, download the trial of Parallels Desktop. The performance there is a whole lot better than VirtualBox, especially for like USB pass-through and things of that nature, which we'll be making heavy use of. But if you can just get it open in VirtualBox, you will at least be able to follow along. And I'll show you the tips and tricks for maximizing your performance when we get there. Ditto Tiny FPGA. Long story short, install Atom, follow the instructions at that link. If you just Google Tiny FPGA BX setup instructions, that's what I followed. And then clone the repository that I linked for this project. The long and short of the code is that it spins up a PLL and attaches some signals to some pins. It's not very complicated. Do your best not to poke through it yet, because like we'll have fun modifying it and whatnot later. Okay. So a little bit of a background for what we're trying to accomplish here in the first place. What is RF compliance to begin with? I'm sure most of you here already know on the basis that you're interested, but every electronic product spams a bunch of RF interference out into the environment as a simple byproduct of operating. Obviously, some of those signals are very deliberate and have a specific function, like Wi-Fi. A camera or a laptop or whatever it is, a cell phone, has a Wi-Fi radio. It emits signals. Those affect other devices nearby in a very calculated and specific and standardized way to make things happen. Well, it turns out you can do that same emitting in a not calculated and not standardized and not anticipated way that breaks things. So the whole point of RF compliance is testing to make sure that you're not falling into that category of device. And in particular, and I apologize, this is a very global conference, and I do not know global rules. Also, I should back up and say I'm certainly not an expert in this. This is my recent experience going through this myself, with some novelty added on top. I know only FCC rules and only vaguely. There is basically a corollary to all of this in every other country on Earth. So your own rules will vary, but they will probably look pretty similar. So in particular in the US, in the FCC specification part 15, subpart B governs unintentional radiators, which are devices that don't have a wireless communications function or anything like that. They're not intended to create RF energy. They might cause accidental or incidental interference with other devices. And then FCC part 15 subpart C governs intentional radiators. So this is the certification that you have to get if you have implemented a wireless protocol or radio and intend to broadcast effectively loud RF signals. How does testing work? So when you actually have to go through the process of getting a Part 15B or Part 15C certification for your product, what actually happens when we try to do that? Well, you Google around online, you find a lab that advertises it's capable of UL testing, and you send them your product, and $3,000 to $30,000 later, they send you your product back and a piece of paper that says you did not pass your test report. To get to that point, they put your device inside a big Faraday cage, just a wall or a room full of metal walls so that no external signals can leak in. They point a big expensive antenna at it, and they turn it on and spin it around on a Lazy Susan on a wooden table. I think the tables are probably expensive too, although they don't have to be. And then they measure that antenna with a big expensive spectrum analyzer. And I'll touch on why it's big and expensive, but at least for our purposes, you don't need to approximate this setup. So the real point of this setup is it creates a calibrated and baselined test report that says your product is emitting exactly this much energy at such and such a frequency, and that is above the limit. That's where you have a problem. And basically all of the money in this setup goes into actually having calibrated output. So what happens when you get this test report back? Well, you probably failed. You get back a sheet that looks like this, and you have to figure out why you failed and what you're going to do about it. So at this point, you're probably terribly confused. You probably had an inkling that your product was going to fail, but you knew that spending $3,000 for a Part B certification was like the first step to figuring out what to do about it. But now you're a little bit confused. What does this test report actually mean other than that red line crossing that teal line is a little bit scary? Oh, you guys can't see my pointer when I'm sharing this window, can you? You can? Okay, cool. That makes things easier. Obviously, where the red line crosses the limit line, that's not great. Something has gone wrong. But it isn't actually that straightforward what to do about it or how to even read this report. So like, let's look at what this report is actually saying from the get-go. So first things first, there are a couple of different standards for testing. There is measurement distance and which range of spectrum you're trying to measure. So in this particular case, this section of the test report is covering the frequency spectrum from 30 megahertz to 1,000 megahertz, the sub-gigahertz region. And this is specified at 10 meters. So basically the receive antenna is 10 meters away from our product while they're spinning it around on that table, which means mostly it just means that this is the limit line we choose. There's also a testing regime at 3 meters with a slightly higher limit line. But as far as I'm aware, most people use 10 meters for this certification. That antenna, being an electromagnetic device, has a polarization. It's I guess, horizontally or vertically polarized depending on the physical orientation of the antenna. In the last slide, you can see that it's clearly got some asymmetrical geometry to it. So one of these lines was taken with that antenna rotated vertically, and one of them was taken with that antenna rotated horizontally, and you have to pass both of those tests in order to pass your test. So let's look at what the actual tabular data of this report says. And by the way, this is for a real product that obviously failed, and I'll dig into why a little bit. It's a little bit scary, at least reading this test report the first time, because obviously this red line crosses the limit line in a bunch of different spots. So up here in the debug frequencies list, we see there's a worrying peak at 36-ish megahertz. So that's like this guy. There's another one at 70 megahertz. So I think that's this one. There's another one at 250 megahertz. That's these two big peaks, and so on and so forth. So, okay, we've got to go figure out what on our product is emitting RF interference at those frequencies and tamp that down, right? Well, not exactly. So the way this test report is generated is sort of in two steps. I told you that you use a big, expensive spectrum analyzer to measure this, right? For a little bit of background about spectrum analysis, in case you aren't super RF inclined, I don't know how many people watching will be or won't be, so bear with me if this is old hat, but measuring the frequency domain of a signal you can do a couple of different things. Like your test equipment can take a couple of different tactics to measure that. For time immemorial, the only practical way to do this is basically make a device that measures the received power at a specific frequency, and then just tune that specific frequency through time, ideally as quickly as you can, but listening to this frequency, then move to the next frequency and listen, then move to the next frequency and listen, and so on. That's swept spectrum analysis. This first phase of the test, where it lists debug frequencies, is sweeping the spectrum analyzer across the entire spectrum and looking for only the peaks at each point. So looking for the absolute maximum value of RF power that we see for every point in that spectrum. Well, devices behave differently throughout time, and maybe your device is chirping really loudly for a moment. Oh good, my camera's charging, sorry. Distracting myself. Maybe your device is chirping really loudly for a moment, but it doesn't do that all that frequently. And like maybe your device only makes a loud burst of 250 megahertz when it first turns on or something like that. Or maybe it does it for 1 millisecond every 100 milliseconds. And it turns out that doesn't actually really cause any interference on any adjacent devices. So even though the peak is really high, the power that matters as far as causing interference isn't actually that high. For those of you who know what you're talking about in RF, this is about the edge of my experience and knowledge here, but the gist of it is that the first pass of peak detection gives you an idea of where to look for potentially offending and failing signals, and then you go back and do what's called a quasi-peak analysis, or rather quasi-max power analysis. I don't even know if I'm saying that right, I'm sorry. Where, okay, we see in this particular device that there's a really, really bad peak at 250 megahertz. So let's flip the spectrum analyzer into quasi-max analysis mode. We listen at just that relatively narrow bandwidth and move the product all which ways until we can, say that it's either emitting or not emitting an offending frequency at a certain power, and then move on and do the next one instead of sweeping quickly past and just taking the peak. For this particular product, what we see is that the peaks out here, this 36 megahertz peak, the 70 megahertz peak, and all the rest of it, those aren't actually violations from a standpoint of passing or failing the report, passing or failing the test. They're worrying because they should not be that high, and it would be good if we could bring them down below the limit line. But the only one in here that actually exceeds the limit line on a quasi-peak analysis is this 250 megahertz peak, and that's the one that we really need to focus on. And I guess I jumped the gun describing all of that because the next slide was, or did you actually fail? And the answer was on a lot of those peaks, no. This is an example from that same 30 megahertz to 1 gigahertz spectrum, where the product has at least one, actually in this case, there's only one limit line violation at that 250 megahertz. It's still a problem. There's only one limit line violation, but under a quasi-peak analysis, quasi-max analysis, that particular frequency isn't actually failing. So it could be that you've got a bunch of these debug frequencies that are a problem, but it didn't matter because on all of the frequencies that were formally analyzed, you don't actually emit enough power enough of the time to fail. And this brings up actually a critical aspect of testing, which is that your device operates in different modes at different times. And in order to have an accurate test, you do need to run the device under all conditions for the test that it might possibly encounter in the real world. So in particular for this device, it's a PoE powered device that can also be powered by DC. So there's one power condition that may or may not be true. And then because it's Ethernet, it also involves a wireless backhaul. So you can choose wired Ethernet or wireless, which means there are 4 total sort of test conditions. And it turns out that this device performed just fine under wireless conditions because, there may or may not have even been an Ethernet cord plugged in. And as I'll describe later, or right now, I guess, this device basically only fails its emissions testing under connected to Ethernet conditions. So yeah, you have to be very careful about whether your test scheme actually exposes all of the potential failure modes in RF testing, and also make sure that your firmware isn't doing something stupid that it doesn't actually need to violate those. Which, speaking of contrived stupid firmwares, that's what we'll see later on the tiny FPGA, where, okay, this device, is super simple. How could it possibly fail emissions testing? Like, what's going on? Well, if you do something super dumb in firmware, or if there are mistakes that you can make that you can potentially rectify in firmware that will cause an emissions test failure because you just didn't need to be generating as much noise and you didn't realize you were, because, this is sort of a foreign world to most designers. And that was the point here. So not in this mode anyway. This is yet another test mode of that same device where there are clearly a bunch of debug frequencies, and clearly a peak that, at least in the vertical antenna orientation, doesn't, violates the limit line. But in that quasi-max analysis mode that actually matters for passing or failing a test, this product actually passes. So then the real question is, once we get this test report back and we know, okay, we're actually failing at 250 megahertz, or we're actually failing at 900 megahertz, or like whatever it is, what do we do to figure out how to fix that? One, you can just fiddle with firmware. So, let's say you have an oscillator, like you got an LED that blinks at 12 megahertz, or I guess 12 megahertz wouldn't matter. An LED that blinks at 50 megahertz or something, which it turns out we do. We'll get there. Why do you need to be doing that? Just turn that off in firmware and boom, suddenly you're passing. Obviously, people don't go out of their way to do stupid things in firmware, so this is not really a great place to start your exercise. And more to the point, you still have to have a point of A/B comparison. Test cells, plenty of testing houses will let you come in and do live debugging and measure your product while you're making physical changes and firmware changes and all the rest of it. But it's super expensive. Like, time in a test cell is not cheap. Metal walls cost money. So it's best to figure out what you can figure out about how your device works and what might be causing the problem on a bench, before you get to that point. If you know what you're doing in terms of layout, then you can take a look at the actual layout that you committed to PCB and see, like, maybe I've got a bunch of stubs that radiate. Maybe I've got a bunch of like little net antennas. Maybe I've got, weird devices attached, or like ground plane splits under differential traces, or any number of things like that that can cause, signal integrity issues or whatever. Those can also cause RF emissions issues. And I won't really dive into that because I don't want to dive in deep on customer hardware that I actually have test data for. But you can imagine things that cause signal integrity problems normally, like split ground planes where return current on a high-speed trace has to then go around in a big loop around your ground plane split and take a different path to the pin than the data trace itself. All of those sorts of situations can also cause RF emissions. So like, they can be somewhat easy to spot. And in this particular case, this product went through a revision where the layout of a LAN chip on board got really bad. And there are a bunch of obvious ways in which the layout is deficient, and a bunch of obvious fixes that do, in fact, drastically change this RF emissions playing field. But you don't necessarily know that. And more to the point, if you knew exactly what you were doing with layout and could spot those kind of errors ahead of time, like, we probably wouldn't be here. So it's good to give it a once over, but you probably don't know what you're looking for. And if you do, you probably don't have that problem anyway. So then really the sort of first line of defense, which is what this workshop is all about, is near field probing, which is effectively waving a magic wand around your product and trying to figure out where noise is coming from. And like, okay, what does near field actually mean? Well, RF emissions compliance testing is a far field far field test. Like an antenna measures RF emissions in the far field, which again, this is operating at the limit of my RF experience, but effectively boils down to, are you inside of one wavelength or outside of one wavelength? And another way to look at this is, what impedance is the signal in question actually impacted by? Is it the impedance of free space as it floats through the air, or is it impedances as measured close to your board, like the impedance of copper in a trace, or the impedance of the trace to your ground plane, or those sorts of impedances? And the real key point here is that in that super near field, especially like the closer you get, the more the magnetic field dominates, which we'll see when we sort of choose which probes to go for. So effectively, you hunt around on your board for probes that sense magnetic field, and wherever there's loud, high intensity magnetic field, that's probably where you need to be looking as far as what's causing the emissions problems and what you might be able to change in firmware, or what you might be able to change in layout to do something about this. Even in as far as near field probing is concerned, there are sort of two techniques to do it. One of which is, I'll call it the magic wand method, where you grab a bunch of probes that look like this. And there are tons of videos online. This technique is not very tricky, as we'll see. It really is kind of just as simple as it sounds. And it's just setting it up and having experience and doing with it that gives you the valuable, experience. One of the two methods is basically just waving a magic wand around your board that senses those magnetic fields and seeing where the magnetic fields get loud, which basically means get a spectrum analyzer, get some near field probes, and wave them around your board to try to figure out what's going wrong. And like, that's exactly what we'll be doing. Another method, if you really want to spend lots of money, and it does have serious pros, is buy a device that waves thousands of magic wands around for you, and in particular doesn't actually wave them, but keeps them in exactly the same spot. So this device, called EM Scanner from YIC Technologies, basically is a grid. I don't know how large it is, but it's a bunch of antenna elements. It's like, I don't know, 80 by 100 or something like that, little tiny near field probes embedded in a workbench, and it has a spectrum analyzer attached to it, a USB spectrum analyzer that rapidly switches between all of those different antennas. And the idea here is you can run a spatial scan over your entire board and make a little change in firmware, or snap a ferrite on a power lead or something like that, and then test again and get a direct A/B comparison. So this is really valuable, but it is the expensive way to go about doing things. And I think it's super interesting. I've never actually tried it myself and don't have the money to, but if you want to learn more about it, the link up at the top of this slide, if I've done it correctly, should be to a webinar I saw recently. It's basically advertising material for this device in this company, but aren't they all? Super interesting to see exactly how it works and what kind of A/B comparisons you can make with a device like this. It turns out the predecessor to this kind of a device for doing really rigorous A/B comparisons is effectively a robotic arm that just waves your near field probe over your product the same way we'll be doing manually. So at this point, I guess I would love to kind of check in with everyone, how everyone's doing on software. I'm kind of through all of the talking theory, whatever stuff that you may or may not have just ignored. And if everyone's still really far behind, like catching up, setting up software and everything, maybe I should take a quick slow down here. Maybe not. I don't know. I can't see the chat for whatever reason. Do you guys have a read on how that's looking? Fine. All right. I suppose I'll carry on. Effectively, the quick demo here is, if you have tons of money, how do you do this sort of near field probing, quote unquote, the right way? So basically, I've got here on my bench, we rented for this RF debugging process, a Tech RSA 507A, which is a real-time spectrum analyzer. Oh, I guess I should cover that too. And then these Rohde & Schwarz HZ15 probe set. as far as the RSA, so I told you guys about swept spectrum analysis, where you look at one point and then move to the next in frequency and then move to the next in frequency and do that in a sweep. We can demo that with SDRs a little bit later, but the alternative to that that's basically only possible with modern instruments and tools is real-time spectrum analysis, where effectively you take a time series sample of a chunk of spectrum and then analyze it all at once, do an FFT on that time series data, and that gives you a frequency spectrogram of what's going on in the RF at that moment in time in that whole bandwidth. So SDRs do exactly this. Rather than sweep one frequency through, the RTL SDR we'll be using takes a 2.4 megahertz wide chunk of spectrum all at once, centered around your tuning frequency, and reflects that all at once, which is super great for zeroing in on a frequency that you already know is a potential problem, because you just tune to that frequency and then you can see in real time as you move the probe around exactly what that frequency is doing, along with potentially frequencies adjacent to it. It's a little bit of a mixed bag, but the cool thing about the RSA 507A, like a serious real-time spectrum analyzer that you spend good money for, is it does all of that really fast and will also do quasi-swept stuff where it takes a chunk of spectrum, a chunk of spectrum, a chunk of spectrum, and shows you what happened during that sweep with subsets of real-time spectrum. We'll see that in the demo now. And we can also approximate that with our SDRs later, which I will get to as well, and which is why we're using Q Spectrum Analyzer. So let me switch. Oh, I guess I should cover these probes too. The two types of near-field probe that exist are H-field and E-field probes, one of which senses the electric field in a piece of space, in a volume of space, and one of which senses the magnetic field in a volume of space. So this is exactly the same way that a voltmeter senses voltage and a current clamp senses current by virtue of magnetic field. We've literally got a current clamp that uses air as the core in the form, or for all of these H-field probes, and we've got I don't want to say electrostatic, but basically a voltmeter operating in air, which is a little tiny antenna on the end of each of these E-field probes. And the only difference between the probes is the spatial resolution. So the small E-field probe and the small H-field probe sense a much smaller area, much smaller volume of space with much lower sensitivity. So a probe, this large probe will react very sensitively because it's capturing a lot of magnetic field, but you won't really know where that field is coming from with quite the same spatial resolution as a tiny one. And the real point of this is with the SDR and low noise amplifier, the sensitivity problem isn't actually a huge concern. We can amplify the signal up until we can see it, even though the sensitivity of the probe itself is very, very tiny. So the beauty of that is we wind a really tiny coil, and then we get to see exactly what's happening on, for instance, an individual trace. So I am going to find where Zoom went. I legitimately don't, oh, stop share. There we go. That's the problem. And let me share my virtual machine. Y'all should be able to see a silent spectrum of this Tech RSA. Let's see if it will actually run. Continuous, you don't appear to be running. Is it still connected? Oh goodness, it might not be connected. Sorry. All of my all of my Bluetooth devices disconnected when I moved my laptop. All right, so I'm connecting. I just passed through the USB device to this virtual machine. There we go. Okay, so what we're looking at here is I've got the low noise amplifier hooked up to the input of this actual Tech RSA, and I've got the near field probes plugged in on the other end. The reason I recommended this particular LNA is that you can power it via USB or bias T or external DC input, so it's easy enough to move for this situation. And what we'll do is I am going to attach this bigger B field probe, H probe, I guess, And we'll take a look quick at this Alcatree board that I've got just because it's interesting. So you'll notice that we're scanning from 0 megahertz to 100 megahertz. It's a little bit confusing that this isn't a logarithmic plot. It's linear. But 0 to 100 megahertz, because I figure that's probably where we'll see something along the lines of clock signals or oscillators or anything like that. You know, we'll generate higher frequencies inside the FPGA, but board level stuff, that's probably where we'll see. So if I start just waving my magic wand over this entire board, well, we see a lot of stuff going on. We see a lot of really broadband noise if I get super close to this switching converter, which, like, I guess probably shouldn't be too surprising, right? Like, switching converters make a lot of magnetic field noise, and that's what we're picking up. And this is one of the key areas where the difference between near field and far field is important. The fact that we're detecting all of this noise doesn't necessarily imply that this noise exists in the far field electric field. So like, this might be cause for concern, but it's not actually, because we know that, you know, it passed the test report. Actually, for this device, we don't, but I assume it did. I mean, it probably didn't. I don't know. Anyway, we don't necessarily have to worry about it. What's more interesting is there any like individual sharp peak that we can pick up? And it looks like on this side of the board, I'm not seeing anything that's super obviously like a clock or an oscillator. I kind of figured that this device down here might be an oscillator for the FPGA, but I'm not so sure. If we flip the board over and search around, it's pretty quiet up on this end. Ooh, but there's something. That's certainly a little bit interesting. We're starting to get a nice bright peak. Is that 60? Yeah, 60 megahertz. We're getting a whole lot of 60 megahertz right around this area. So like, let's go look at what that might be. And then if we come down here, we start to see a couple of other individual peaks. I see them now because I saw them earlier, but they are a little bit buried in the rest of the switching noise. So, okay, we've got some 60 megahertz somewhere over here to look into. We've got a little bit of peakiness down here. It looks like, what, 35, 36 megahertz, something like that. So let's go in for a slightly closer look. I'm going to switch from the like large B field probe that I have been using to a slightly smaller probe that gives a little bit better spatial resolution. And we see again, okay, I mean, the peak is lower because we're using a less sensitive probe, but we definitely see that same 60 megahertz peak. We don't see a lot of that broadband noise, which is interesting. And then we see, I'm just going to give it away. It's a 12 megahertz and a 36 megahertz peak down here if we get close to this thing that looks suspiciously like an oscillator. So just for giggles, I'm going to throw this all under the microscope and have a look at what we're actually looking at. And especially, like, if you're debugging your own design, it should immediately be apparent what you're looking at because you'll know. But lo and behold, this is an FTDI FT232H, serial converter chip. If we look up here in this corner, that thing that looks like an oscillator is indeed a 12 megahertz oscillator. So it sure looks like we're picking up 12 megahertz and a couple of harmonics of it. And okay, what's going on over here? That's a little odd. Let's dig in on that a little bit before we get too much farther. I'm going to switch to this tiny, tiny little H-field probe. And if this looks similar, for those of you who followed along at home to begin with the really small DIY probe you might have already made, the whole point of this probe is that it's the same loop antenna, the same magnetic loop antenna, but in a tiny, tiny little package up at that tip. So we should be able to see, if we wander around with the loop parallel to the board, we can see, okay, that 60 megahertz seems to be over here, and it's not actually over here anywhere out in the free space. It's not as bright down here by the oscillator. If we get really close to the oscillator, we can see that 12 megahertz and 36 megahertz really pick up. But if we get over here, oh, something's going on right around here that 60 megahertz is really picking up. So now the question is, okay, let's look at what trace that might be on. If we move the probe orthogonal to the trace, so like we're basically putting half of a current transformer like next to the individual trace we're trying to measure, we can basically, with this probe, pick out nearly which pin specifically is actually emitting all this noise. And interestingly, we can see some new and interesting noise on other pins, individual pins. But that's what's going on over here. So at this point, we have a halfway decent idea of what noise sources exist on our board and what's going on. And let's just assume that you were looking in this range because you had a 60 megahertz failure in your test report or something like that. Although you can just hunt arbitrary signals this way. It's just if you don't know that they're failing yet, then it might not be worth your effort to try to correct them. But sure enough, we've got those loud signals. Let's see what they might be. If we look over on the data sheet for the FT232H, I guess this would be easier. I am just going to open this in a tab. Well, it might be easier unless my virtual machine completely chokes and dies on it. Oh. Nope. I guess I don't actually have, I'm just trying to rejoin this chat. There we go. Didn't copy it the first time. If we look at the data sheet for this, multiple choices, what? Oh my goodness. Oh my goodness. Okay. Well, anyway, long story short, if we look at the data sheet for the FT232H, we see, one, it does indeed use a 12 megahertz oscillator. So that thing that had 12 on it and looked like an oscillator was a 12 megahertz oscillator. Surprise. It also has a couple of interesting features where it pipes clocks out on a couple of different pins. So it has a couple of different clocks that it'll pump out. I don't recall exactly what they are, but one of them is a 60 megahertz system clock that all of the other devices in your system are supposed to be synchronized to. If you've got, I guess, multiple devices operating on that same, oh, sorry, didn't mean to bring up the news. If you've got multiple devices operating on that same circuit and you need to time synchronize them, it blasts a 60 megahertz clock out on one of those pins. So that's probably what we're spotting there. And now you just go look at the pinout for the device and see, okay, is that what I'm seeing? Is that signal that I know exists in another part of the chip coupling on to that signal that I was measuring erroneously, or what's going on here? Let's see. And another interesting feature of this, I don't know that I can demo it because I don't think, it seems like it's going to be a lot of work to try to set up a computer audio pass-through. But one thing that this tool does offer that's kind of nice is if we go to displays and do amplitude versus time, maybe? Doing this live is probably a poor choice. I think this is correct. Why are you not even running? Acquisition bandwidth too small for current setup. Oh, I want to measure minute. So this is one of those aspects. This RSA has a real-time bandwidth of about 40 megahertz, which means if I'm looking at this spectrum view, it looks like it's one continuous spectrum that it's capturing over and over again, but what it's actually doing is capturing the first chunk, then quickly changing tuning frequency, capturing the second chunk, and so on for the width of my bandwidth. Some devices require, some software tools in this suite require that you aren't exceeding the real-time bandwidth. It requires, it can't sweep and sort of dither sections of frequency spectrum that are coming in. So this tool is one of them. This amplitude versus time has a convenient tool. I don't even remember where it is, but you can effectively turn on like a squealy signal output. I'm sure I've just got the wrong tool, where as you are over a particular frequency of interest and you see the spike, it'll basically make a whistle that gets higher in frequency with higher amplitude of that section of spectrum and lower. So that instead of having to stare at a screen while you move your probe physically around, you can listen audibly for where the signal happens to be loudest, literally. I don't want to dwell too much time on that. One thing I do want to demo is if I tools, presets, setup, displays. I want a spectrogram view. So in particular, oh, do I want a spectrogram view? Goodness me. I want DPX. That's what I want. Remove you, add DPX. Okay. So DPX is Tektronix's version of like digital phosphor. And the idea here is that the color corresponds to the effectively average amount of power at that frequency. So clearly we've got some peaks up here, and that's the peak line that we're detecting. If we look down in traces, we can see trace 1 is the positive peak. So that yellow trace is the absolute maximum power that it detected in that period of time. This basically colors the average power. So we see that the average noise floor is actually a little bit lower than the peak noise floor, which makes a lot of sense. If I want frequency 50, span 100. And actually you can see it here where it appears to fill in this part first, then this part, then this part, then this part, then this part, then this part. Because it's trying to capture all that statistical data, so it takes a ton of captures at a particular tuning range and then moves on to the next one and then moves on to the next one, we can really see the sort of sweep action that it's doing, and we'll be able to see this later in SCR as well. But this gives us a much more interesting idea of, if I go over here and measure, let's say that 60 megahertz thing, that gives us a real interesting idea of what's actually happening on that signal where, okay, the peak that we were measuring earlier is very indicative of how much RF power is actually going on there. And you can see why this gives you a really good visual of what's going on if you are operating in a frequency range where you can tune to it. And we'll see later, while the other tools don't necessarily scan the frequency to give you a wider than real-time bandwidth like this, at least SDR Angel does give you this sort of digital phosphor view that can be super useful if you're looking at a range that's relatively more constrained. Let me figure out where I am in the slides. Okay, so at this point, I want to stop burning a bunch of bandwidth on that. Let me close that VM and go back to sharing the slides. Yes, that'll do. Okay, so I should be back to the slides. So at this point, I want to like actually quickly build a probe and show you that process. So like this will be a little bit of a catch up before I dive in with the SDR side of things and show you how that compares versus the expensive RSA gear. So I showed you before this probe, which is like basically my favorite of all of them. This probe is literally the same as this guy. It's just a loop of wire tucked up neatly and tightly into the tiny little tip of that plastic housing. So if this might be impossible to see, and I preemptively apologize if it is. If this is roughly equivalent to this guy, albeit without any shielding, then these two are roughly equivalent. And really all we need to do is make a loop of wire as small as we can possibly get it. And there are a couple of key differences that I've found in practice don't appear to actually matter all that much. One key difference is it's really important where the active area of the probe is, and the definition of active is where there is and isn't shielding, at least nominally. So like this probe is designed in such a way that there's a magnetic loop up here, and this is sensitive to magnetic field through the probe, like through that open loop, but not at all incident electric field, because like you're trying to measure just the magnetic field. You don't want this whole thing acting like an electrical antenna and receiving electric field as well. So this probe is designed in such a way that there's a shielding, a conductive shielding over the entire thing, though split so that there's still a current loop for magnetic field to induce a current and therefore a voltage. It turns out I think that's actually not altogether that important, and at least it's not important enough to spend that money on these probes if you don't desperately need them. I think what's going on here is that this probe, which is just the simple loop of wire, the way it's designed is we've got an actual open loop of wire up here at the top. You can see it's actually technically two loops. I'll just open it up like that. We've got an open loop of wire up here at the top that magnetic field can penetrate. If we look down here, the probe theoretically should be insensitive to any magnetic field in this region because, one, the loop area and the induced voltage is proportional to loop area. The loop area is really tiny on any of these individual little twists. And also they alternate direction each time. So it's effectively if you wound a transformer one way for one turn and then the other way for the next turn and then the other way for the next turn and then the other and so on, so that basically every turn just canceled itself out and the net output of the transformer is 0. That's effectively what we've done here by twisting this pair, is both minimize the loop area that's open to magnetic field and also make sure that any magnetic field affecting this open loop is immediately canceled by the adjacent open loop. And then the second half of this is, I think these pretty much just don't really require shielding to be useful, simply because they're like electrical short circuits at DC. So, you know, this will have like terrible rejection in an RF sense, but also terrible sensitivity to electric fields. So we're basically just relying on the terrible sensitivity to E fields of a probe that just has a short circuit to ground effectively, and measuring primarily magnetic field instead. So the way I made this probe, obviously it's magnet wire capped on tape and an SMA connector just taped onto a regular garden variety wooden skewer. I've got my magnet wire here. What I did was, I hope I have this pin here still. Oh, I originally wound this on a pin, but we'll just grab some sewing needles out of my thing instead. What I effectively did was clamp a needle in a vise, get it nice and tight. Stabbed myself a couple times, true story, legitimately drew a fair amount of blood doing this, which like is pretty predictable if we're honest. Let's clip off a bit of wire, and literally this is all there is to it. One wrap of wire, pull it nice and tight, and start twisting. And we'll see, this probe is not great because there's a big open loop of wire next to the active tip. Try to tighten that up, but really that is all there is to it. And what's interesting is this basically gets you for approximately free almost all of the benefit of that expensive HC15 probe set over something like this. So, you know, near field probes don't have to be expensive, and they've been getting cheaper lately with the sort of hacker focused products from like RF Explorer and whatnot. These near field probes are great. They behave and operate nearly identically to these probes. Like, it's basically just quality of life difference between these two. The SMB connector on the base of this is really nice for just chunking in and out of the cable when you switch probes frequently. RF Explorer gets around that problem by having this little piece of rigid coax and an unthreaded SMA. So you can just slot those into the top. I find it's, one, a little bit fiddly, and two, there's not much room to grab on the probe. So I bought a couple of SMB connectors after the fact and added them. I guess actually I bought these SMB connectors so that I could just use this cable to go back and forth between these two probe sets while I was working. But I encourage, if you're making probes, probably use SMB connectors, you know, with a handle just to make things easy on yourself. But you don't have to overthink it; they'll still work. And really, the beauty of this probe over everything else in the RF Explorer kit is simply that the smallest probe in the RF Explorer kit still has a bunch of bulky shielding around it, so you can't really dive into an individual trace. Yeah, so obviously I didn't do the soldering. I'll try to go a little slow if anyone's trying to catch up, but that's really all there is to it, to build a a near field probe that is genuinely extremely useful for figuring out exactly what trace or signal or subsystem on your board is causing noise. Because it's not necessarily enough to simply wave your magic wand over. So in that design, it was the LAN 9512, right? The LAN 9512 was radiating all of this 250 megahertz noise. It's not enough to just wave your magic wand over the LAN 9512 and say, huh, it's the LAN 9512 making 250 megahertz. There's no thing in the data sheet for that part that says, this part will radiate 295 megahertz like a banshee off of this pin, figure it out. Like, they don't offer you that kind of guidance. It turns out, like, the Ethernet subsystem on that chip operates at 250 megahertz, and there are a bunch of different analog voltage rails and like conditioning pins where 250 megahertz is coupled very strongly onto them. So if you have like large loop areas and long traces and decoupling capacitors that are not super adjacent to the pins and that sort of thing, that's what you end up with. Oh, and I'm actually on my last slide anyway, I guess. So yeah, basically the outcome here is when you've got a signal that you know what you're looking for, you want to use something like this really tiny probe to find exactly which pin it is. So let's go ahead now that we have a probe taken care of and we've got all of our RF stuff set up. Let's go ahead now and actually fire up the RF toolchain, or sorry, the SDR toolchain, and see about doing this the cheap way. There we go. For anyone wondering, the Dragon OS VM username is Dragon, password's Dragon. Yeah, log in. Okay, so first things first, let me get my SDR device and actually plug it in. I got this guy, the one that I recommended all of you buy. I have to plug it in over here because USBs are at a premium. And then I will go over here, pull my Vanna off here. I'm going to be, this is a critical aspect that I didn't cover. I covered this in the instructions, but the way we'll be powering this particular LNA is via a bias T. So I didn't want to like offer a shopping list with a bunch of USB power supplies, even though I'm sure everyone already has one anyway. I wanted something that was easy. Basically, a bias T works by setting a DC voltage on the like input to the SDR, and then this device is powered by that offset voltage on its output side. So if we plug this guy in, so output to the SDR, it will light up with power because the bias T inside the SDR is powering it. Very critical point here is that there's a DC voltage on this pin out of the SDR right now. So what we definitely don't want to do is plug in our probe without the bias T, or rather without the LNA. The LNA has a DC blocking capacitor on the RF input side, so that no DC voltage from the power supply circuitry of this guy leaks out into your antenna or anything like that, which is important because these are DC shorts to ground. So effectively, if you plug this antenna directly into the bias T enabled SDR and you have no way to turn the bias T off, you're just pulling tons of current out of the bias T. This SDR device can handle that for a brief period of time, but you basically overheat the linear regulator that powers that circuit, and after a few seconds or something like that, it will eventually burn out. So yeah, make sure you use the LNA between this device and your probe. Let's go on the other side, and let's plug in this guy. Now, naturally, you can follow along with the probes that you have. I suggest you make a couple of different probes with loops of different sizes, all that sort of thing. Oh, my apologies. I absolutely can stop screen share. Good call. Wait, Can I stop screen share? Can I only choose a different screen? Have I stopped? Okay, cool. Taken care of. Yeah, apologies about that. And also it's a GoPro, so my apologies that I'm not like rapidly switching lenses to make it more obvious. It's just enough of a challenge as it is. Oh, I guess I'm actually gonna have to share my screen in a second anyway, but yeah. I would make a couple of different size probes and start with this one while we search around. But in the meantime, for now, I'm just going to go ahead and fire up my SDR virtual machine, and you can see what's going on. So first things first, if you've got your virtual machine open and running, you want to pass through your SDR device to that. I'm running Parallels, so this happens automatically because its performance is just a little bit better than VirtualBox. VirtualBox kind of crawls to a halt, and I'll show you how and why. So go up to Menu, Devices, pass through your RTL SDR device, and that should be reflected. Yeah, so my RTL SDR is passed through. Let me actually share my screen now. Zoom. Share screen, Parallels desktop, share. Okay, there we go. So I've got my RTL SDR plugged in. It's passed through. My virtual machine isn't responding to, oh no. Oh no. There is one problem with Dragon OS LTS, at least in Parallels. I don't know if this problem will persist with your running this, if you're running this in VirtualBox, but if Dragon OS goes to sleep, mouse input doesn't work when it comes back out. So we can see my desktop here, it is not accepting any mouse input, and suddenly the clicks will all flood through as soon as I guess sleep and re-wake this device. So instead, I'm going to go restart this guy, force restart it, and hopefully that will come back nice and cleanly. Bear with me. There we go. Okay, cool. There we are. Okay, so first things first, we're going to fire up. I guess let's start with Q Spectrum Analyzer. No. I'm going to fire up SDR Angel. So let's fire up SDR Angel. It's under the Internet menu down here. We'll load this. If you're using a different version of SDR Angel, I think this interface actually changed slightly. So down here under Sampling Devices Control, RTL SDR is automatically selected for me. If I click the finger selection icon, I don't know what it is, you can pick from other devices. I don't have anything else relevant plugged in right now, so it won't be a problem. I'll hit cancel. That menu is like a button up here or something in maybe a newer version of SDR Angel or an older version. I'm not actually even sure. But I know I've selected the right one here, so we'll go with that. Recall that this is not operating as a swept spectrum analyzer. This doesn't have anything like that. So the sample rate affects the maximum bandwidth span, where previously I was setting that span to 100 megahertz and setting the center frequency at 50 megahertz over on the RSA. Right now, I've set the center frequency at 100 megahertz, 1,000 or 100,000 kilohertz, 100 megahertz. The span is set by the sample rate. So we've just got a 2.4 megasamples a second, which is a 2.4 megahertz bandwidth. It's I and Q, so Shannon is, or Nyquist is satisfied. But anyway, I am going to throttle that down for now because I fear that this virtual machine isn't going to keep up. I actually don't, but yours might not. So let's go down and knock that sample rate down to 950 kilosamples a second. And let's go down here in the spectrum display. We can leave the window as is. We're going to switch the FFT to 128 points. We'll show what these toggle later. but leave them as is for now, and we can play with them. This basically makes the FFT math a little bit easier for the VM to handle. So if you're going to run into performance issues, this won't immediately freeze your setup. If you do run into performance issues, it's useless trying to poke around the interface until it comes back. Just exit the SDR application. They're not well optimized for user experience. They're well optimized for doing the math quickly. So what we see here is, cool. We've got that same like digital phosphor view from the RSA, which is super neat. We see that there's a nice bright peak at 100 megahertz. And this is one of the disadvantages of using hardware like this is we do kind of have to question where that peak is coming from. So if, for instance, I completely unplug my LNA, we notice that that peak actually still stays there. So that could be something real, or it could be a an artifact of the actual sampling frequency, like the tuning frequency of the SDR, or it could be something internal to the SDR. Just for giggles, let's try bumping up a little bit and see if that frequency shifts around. Oh, can I even do that? Yeah. So we notice that that peak on our tuning frequency doesn't go anywhere as I move the tuning frequency around subtly. So basically, that's not a real signal. We can kind of just ignore it from this point forward as being a real signal. So in my case, I know that I want to go looking back at that 60 megahertz signal on the Alcatraz. If you want to follow along on the Tiny FPGA, if you've gotten to the point of actually flashing the firmware and whatnot, like flash the firmware and then browse around, basically you can look for the oscillator at 24 megahertz or the signal in question at 50 megahertz, but we'll get there in a sec. I'll show you that board in a sec. Before we go there, I'm just going to quickly retune this SDR to 60 megahertz. And I'm actually also, I know this VM can handle it, so I'm going to crank up the sample rate and everything. And we'll add some FFT bins. This still seems pretty performant. 2K. Okay, cool. Actually, this is an interesting point. When I cranked up the FFT, that peak got very much narrower. So it's probably some unsuppressed artifact of the math or something that I'm just not quite understanding. It's still there a little bit, but obviously it's basically one bin of the FFT that's lit up, so it's bias, and we can thin it out. We do notice that there are a couple of other lines at some even interval, so we're measuring subtly some harmonics of something, but anyway. So let's wave our new probe over that area and look at that. Something's happening. Cool. That's super interesting. Because we have that problem at the exact tuning frequency and we know that this signal is at 60 megahertz, I'm going to drop off slightly so that now, actually I'll drop off very more slightly. So now we're actually interested in this peak over here. This way we're not conflating the signal that we're actually interested in measuring with whatever like bias point we found. So if we come over here and wave our probe in that spot, we see that really sharp line on that signal and actually some other harmonics going on in there that we didn't see before. So that's super interesting, and I haven't looked into what that might actually be or whatever. If we move around, we see some other nice sharp lines that pop out, and those are very clearly artifacts. And because we've got the spectrogram view here too, we can see that seeing in the waterfall diagram what's going on makes things a little bit clearer when we have such thin FFT bins on this particular screen. Actually, just for giggles, I'm going to make the FFT a little shorter. This will make the peaks a little bit wider and more obvious. So now we're going to recreate the test that we had earlier of, okay, where is that pin in question? I'm going to rotate the probe so that it's basically hoop perfectly projected down onto the wire of the pin. And we're going to wave that around and try to figure out, I guess it's a little bit tough here to see what the actual peak is. and our other tool will show this a little bit better. For any particular case, you basically have to feel around for the combination of settings and tools that work best in that case. What we can see as we get close to this little capacitor that's right here, that capacitor certainly has some serious current going into it at that 60 megahertz mark. And obviously, if I pull away, that line goes kind of dim. If I come in really close, that line is nice and bright. Like, we can really see something going on there. And basically pinpoint which pin it is by figuring out where it's the brightest, where we're moving our wand. Okay. Make that bin even a little bit wider. Okay, yeah. That's nice. So we've basically now built a tiny spatial resolution probe that can show us exactly which pin on the IC is radiating the noise in question. So let's go over and actually do this on the tiny FPGA side. My apologies that my tiny FPGA toolchain is on my actual Mac, so this might get a little bit ridiculous. Let me key myself up for some semblance of success here. And I have to look past the camera too. Oh, there's screen sharing. There we go. Stop share, screen share, desktop 2. Yes, share. Cool. Okay. Let me launch Atom. I'm going to go to File, Open, APIO template. This is where I happened to clone the project. Mine's called APIO template because I just never changed the directory name before I committed it. And we'll just open that entire folder. And then we'll open top.v. You should be able to use the command line like APIO program tool to do this. I decided that making you program a binary from the command line that I didn't give you code for was just too much effort. So instead, I will just, first of all, make sure that my tiny FPGA is actually plugged in. Won't get very far otherwise. Connect that to my Mac. And APIO upload. Tiny, cool. I'm actually going to show one thing quickly before I get any farther. So notice how there are 2 LEDs and one of them is lit brightly and the other one is not. Let me reset this. We see that that bottom LED is now pulsating, right? And it's pulsating between 0 brightness and like the brightness of the LED adjacent to it. When I go ahead and program this, I just, quick program again. Basically, it's in bootloader mode. Now it's actually running the gateware. Notice how it's a little bit dimmer. It's dimmer because I'm just blasting a 50 megahertz signal out onto that LED, which, yeah, don't do that or you won't pass emissions. So now that that's programmed and taken care of, and again, this is where if you're having trouble with the tiny FPGA side of things or whatever, like I would follow the same sort of thing that I did on the Alcatraz board and find a signal of interest and convince yourself what it might be by feel effectively. But we're going to go over and have a look at the tiny FPGA board and see what's going on over there. So I'm going to retune over here. I am going to stop share my Dragon OS. So we're back over here, spinning the waveform. Okay, so we've got 50 megahertz. 50 megahertz is over here. So we already know that I spun up I basically just attached a PLL output on the chip to some pin over here. And if we start waving this wand around, this one has very limited, you know what, we're just gonna start with the big one. Do it the way that we would expect. We know from the test report, the imaginary test report in this case, that we failed on some 50 megahertz noise coming loudly from somewhere. We attach the big probe and start to try to look around where it might be. It looks like it's not down at this end of the board, but it's a little bit tough to say. It's getting hotter. It's getting hotter over here. That's interesting. Okay, so it's getting kind of hot in this area of the board, like centered over the BX. If we move over to the other side, it's still pretty hot. I don't know. It's definitely somewhere up on that top half of the board and definitely less obvious down here. Definitely not the far corner of the board. So it's probably not this SPI flash device. It might be the FPGA itself, but I'm not really sure. It's probably not the USB because 50 megahertz doesn't make a ton of sense. And obviously, as soon as we get up the cable, the shielding, no, it's definitely not that. So it's somewhere around here. Obviously, you already know where it is because I told you I pumped a 50 megahertz signal out to the LED, but let's just verify that. If I wind on this other probe, okay. I'm gonna use the probe. This is the plane of the opening. I'm gonna wave it around above my board the same way I just did that other probe. There's basically nothing to be seen because this probe is really not sensitive and weird. Turns out we're emanating the signal in a very specific spatial region. And this is why you start with the bigger probes, because it'll give you it'll pick up much more and give you an area to narrow in on. If we wave this probe over here though, we start to see that signal perk up, and I'm not quite sure if we wave it directly over the FPGA, it seems to be up there. That's definitely interesting. Ooh, something seems to be going on over there. If we zoom in really closely, I'm going to move this over to the microscope in just a second so that you can actually see. I guess in the meantime, I'll just change the big GoPro lens. Let's see. Wait for it. Okay, well, it's not that much better. If you look closely, we see that we've got a bunch of signal when I'm directly over the FPGA. We've got a bunch of signal when I'm over here in this corner. It actually seems like it probably gets the loudest of anything. And if I move over here, we definitely still see the signal. Over here, we don't practically see the signal. Oh, that's not true. We do see the signal in a couple of spots. And that turns out it'll kind of make sense in a minute. And over here, we see the signal a bit, but then let's do that IO pin trick where I put the probe basically like a projected shadow of the trace that it's on. If I move around, ooh, I start to see a lot of stuff going on. But there is a pin somewhere on this side of the board, right about, this is where having the buzzer actually, I don't know that it's worth the cost, but it's certainly nice. There's a pin somewhere right over here, right about there, maybe? Something like that. That looks a little bit like something going on over here is probably what we're after. Let's have a look at this under the microscope and see what those physical structures are. Now that we've pinpointed them with our tiny little probe, let's see what they actually look like they might be. Okay, so here's the tiny FPGA. Here's that main chip, and up here, well, maybe I should just use my probe as a pointer. Up here is where we saw a bunch of that signal as we were waving around over the FPGA. We saw a bunch right here, we saw a bunch right there, and we saw a bunch down here. We saw a little bit up here. Well, capacitors are definitely suspicious from a radiated noise standpoint, especially when you're looking at current through a trace. Basically what we're measuring is, with the probe right here in this orientation, we're measuring the current through that trace and into that capacitor. So what we've basically measured is that capacitor is sinking a ton of RF current at the 50 megahertz that we can detect with our loop probe, and ditto over here. So what I'm willing to bet is that these capacitors here and here are probably IO bank filter capacitors, and we're probably probably coupling noise onto the IO bank supply rail because we're driving a relatively low impedance device at a ludicrously high frequency. This thing looks a bit like a capacitor as well as a resistor, as well as a diode. So we're really probably taxing that voltage rail pretty badly, and we're seeing it in the form of supply current from these capacitors trying to keep that rail stable. The other thing we might notice is this LED comes over here. Oh, I guess I wasn't even probing in the right place. So it makes perfect sense that we didn't actually see much up here when I was trying to test each of these individual traces, and we did see a bunch down here. I never even got over to the proper place to measure, which would have been this trace running down there on the top side of the FPGA. Just for giggles, let's go back and see what that has to say about things, because we should be able to see exactly which pin is sourcing all of that current. I have to reprogram APIO upload. Still pulsating, still in bootloader mode. Okay, now I got a dim LED. We're good again. Okay, cool. So we know that the pin is up here somewhere. If I stuff my probe, oh, look at that. Somewhere right up along that edge, there's a nice bright 50 megahertz signal. How about that? Cool. So we've isolated exactly where that 50 megahertz signal is coming from. I don't want to spoil the fun, but you can start this now. The sort of Easter egg hunt is this signal is actually being piped out to a different place as well. Somewhere else on this board has that same 50 megahertz signal on it, and you should be able to use this same probe to find it. Because keep in mind, even though there's no load attached to any of these pins, there is a capacitance between the pin and air, and between the pin and its own ground plane and all the rest of it. So we are loading a very, very small value capacitor, or rather piping into a very small value capacitor, a relatively high frequency signal. You should be able to measure a current on some trace even out to just the pad capacitance. So if I zoom around, I guess there's a little bit down here. There's not so much over here. This big loop probe shows that there's noise pretty much everywhere on the board, but your job is basically use that small probe to try to figure out which pin the signal is piped out to. And drop it in chat, not that I think I'll be able to actually read it at this point, but drop it in chat when you think you've gotten it. And when you do, go back over to the code, top.v. And if you know Verilog, see if you can figure out and make sense of where that signal is coming from. And if you don't know Verilog, I guess basically just look for words that look like pins. And you'll probably be able to figure out where it's attached up. And then go look at that trace with your current probe, like with your loop probe, and you'll be able to see, oh yeah, it's definitely that particular pad that's getting lit up with high frequency and not this other pad or whatever. In the meantime, I want to show you the last super cool and interesting tool in our toolkit, which is Q spectrum analyzer. So obviously this is great if we know exactly what frequency we're looking at and we want to figure out how loud that frequency is. It's kind of on my to-do list at some point, but almost certainly will never happen, to add that like whistle mode where at the tuning frequency, at the center frequency in one of these SDR apps, it'll just like power a whistle that increases in frequency and decreases in frequency with increasing RF power and decreasing RF power. So like maybe it's between like 20 hertz at minus 100 dB and 3 kilohertz at 0 dBm. And then you can wave your magic wand around at the tuning frequency and figure out exactly where on the board it is. I'm sure you can probably whip that together with SDR Sharp or GQRX, or not GQRX. I don't know, one of the SDR tool chains. I'm sure GNU SDR. You can probably whip that together in 2 seconds as just like an RF power meter at the tuning frequency. But it would be cool to do it with this same DPO style view so that you can see what's going on around it as well. Oh God. Okay, cool. It didn't go to sleep. I thought that was going to be another restart. But again, this is only really useful if we've got this sort of narrow bandwidth. So let's go try something else. And I guess this would be a good time to interject with sort of the merits of different SDRs. So we've been using this RTL SDR this entire time, and really the only reason we've been doing that is because it's super cheap. It's rarely the best SDR for the job, it's just super cheap, so if you can get away with it, you ought to, because then you don't have to go spend money. The key figures of merit that are relevant for any of these SDRs is, there are basically two that matter most, one of which is real-time bandwidth, and one of which is total tuning range. So for this RTL SDR, the real-time bandwidth is 2.4 megahertz, and the total tuning range is, what, 24 megahertz to like 1.7 gigahertz or something like that, which means that this SDR is not useful for Bluetooth because it can't tune to 2.4 gigahertz, and it also can't tune the entire 80 megahertz, 2.4 gigahertz spectrum. So the 2.4 gigahertz we all know and love for Bluetooth Low Energy and regular Bluetooth and Wi-Fi exists between 2.40 gigahertz and 2.480 gigahertz. I'm sure it's slightly off of that. Anyway, it's 80 megahertz wide, which means that this SDR can't tune all of it at once. So it's not useful for that. And it also is too high. You can only go lower than that. It is useful for something like ADSB, which has a much narrower signal bandwidth and is at a much lower tuning frequency. I don't even remember what it is, like 1064 or something like that, 1.064 megahertz. I don't remember. Anyway, for our purposes, obviously the tuning band of interest is 30 for this test report that I just showed you, 30 megahertz to 1 gigahertz, which the RTL SDR covers nicely, so it's useful for that. And then the question that really remains is, how do we get better bandwidth to actually cover that whole span? So one way is spend more money on an SDR. So this RTL SDR has 2.4 megahertz bandwidth. This HackRF1 has 20 megahertz bandwidth, so like nearly a 10x improvement. This Lime SDR has 60 megahertz bandwidth, so a 3 times improvement even over that. And 60 megahertz is like dangerously close to that 80 megahertz wide, like 2.4 gigahertz spectrum. So like that's kind of neat. Turns out it's not still altogether that useful, but like getting close. It's definitely a lot more useful for certain applications where, like, if you're hunting around for sub 100 megahertz noise, cool, you can see nearly all of it between 30 and 100 megahertz in one capture on this guy. The cooler aspect of this guy is that its tuning range is between like 9 megahertz or 9 kilohertz. I think it's 9 megahertz and 6 gigahertz. So this covers basically the entire practical RF testing regime from 30 megahertz to 1 gigahertz, and then from 1 gigahertz. Technically, the higher range is 1 gigahertz to like 13 gigahertz, but at least in my experience, kind of just ignore it if it's too high, because you probably don't want to go spend, you know, $30,000 on a month on a 13 gigahertz scope, or not scope, spectrum analyzer. And if you do, like at that point, $500 an hour for your RF testing facility is like, okay, fine, yeah, we'll suffer it. Your product probably doesn't have any violations that high unless you're trying really, really hard. At least in my experience, which is limited. Yours might be better. So like each of these devices offers some different aspects that may or may not be super useful to you, like the absolute range of this device, it goes up to 3.6 gigahertz, something like that. So this can cover Wi-Fi and can cover a bunch more interesting bands than the RTL SDR can. It's also transmit and receive, and full duplex transmit and receive. The HackRF is transmit and receive, but not full duplex. Obviously, transmit doesn't matter for us. But these are all things to consider. But yeah, these devices, I'll show you why why one of them is really particularly useful in a moment. The question that discussion started with is, what do we do about the fact that we have a really, really narrow window into the spectrum with this device at only 2.4 megahertz wide? How do we capture more than that? Like, for instance, earlier I was capturing from 30 to 100 megahertz because I figured there might be some crystal oscillators on this board. I knew they wouldn't be above 100 megahertz, but they're probably in that region, right? Like single-digit tens of megahertz. How do we capture all of that? Well, let's close down SDR Angel because it's not going to help. And let's fire up Education Q Spectrum Analyzer. Q Spectrum Analyzer is a program that basically tries to approximate a swept spectrum analyzer using SDR devices as real-time SDR devices. So effectively what it does is the same thing that the RSA was in that mode where it was capturing a chunk, capturing a chunk, capturing a chunk. This does that same thing, although it doesn't do the entire like digital phosphor where it captures a gazillion samples of one chunk. It just captures one and moves on. But it does accomplish our goals somewhat nicely. So if we go up to settings, this is still with my RTL SDR plugged in, change backend to RTL power FFTW. You shouldn't have to change any other settings in here. Sample rate should still be 2.56 megahertz. Bandwidth 0 is just default. Local oscillator, same deal. This is useful if you have an external like up converter or something like that. And we'll leave waterfall history at 100. Okay. Let's do that same test that I was doing before. Well, it might actually be a little bit easier to let's go between 100 megahertz and 102 megahertz. Because we'll capture like a radio station as a demo signal. 100 megahertz and 102 megahertz. If you're running in VirtualBox, this would be a good place to make the bin size relatively large. Let's go with 100 megahertz if I can. Why is my keyboard suddenly not working? Let's go with 100 megahertz bin size. This will make the FFT a little bit saner. Do the interval to 0.01. Basically, this is continue streaming as quickly as you can rather than pausing in between. And just for giggles, I'm going to, oh, I had that checked earlier, never mind. I'm going to do a single shot. Okay, cool. That's a good sign. So I'm gonna click start and we'll see that this is coming in pretty quickly. There are clearly a couple of peaks. This is basically useless garbage. I don't even have an antenna attached to this thing, but its radio is, pretty loud. So if I attach it, that's not going to work at all. Let's just leave it. It should be loud enough to notice. One thing that's a little bit annoying is that it defaults to y-axis scaling. So I'm just going to go into y-axis, click manual, click minus 80 dB for the low end. And let's do 0 dB for the high end. Cool. That shows us, at least on a static view, what's going on. Now, I know this virtual machine can handle a little bit more in terms of performance, so I'm going to click stop. I'm going to knock the bin size down to 10 kilohertz and click start. That's starting to look pretty good. Like, this is clearly a radio station. I guess that's probably what, 10. This might actually be, so another key point of SDR devices is that their internal clocks might not be right. This might be 100.9, and it's the local oscillator isn't actually accurate. On this Smarty SDR, that local oscillator actually should be quite accurate, so maybe I am measuring this correctly. I don't know what the actual radio station is, so maybe it is 101 point. I don't know. It's not 101. Oh, K-Earth 101. Yeah, no, maybe it is 101. My bad. Anyway, clearly this is a radio station. Clearly this is an adjacent radio station. Clearly this is an adjacent radio station. So we're in good shape. We know we can actually measure at least radio stations. I'm going to get aggressive and knock the FFT down another peg. And now we start to get really interesting data. You also notice the frame rate seems to be a little slower, maybe. Tough to say for sure, but we'll stick with this. Now, let's see if we can sweep out the entire FM frequency range. So we're going to go from 87 megahertz to 108, and we'll see what this looks like. Notice it updates much slower. So the frame rate has dropped precipitously. And if I stop it and knock that bin size back up to, hell, let's make it 1 megahertz. So this is going to be super fast to calculate math, right? Notice it still chunks in at like, a frame a second or 2 frames a second or something like that. Clearly the math isn't the problem. What's happening here is the SDR device itself is tuning to this frequency range and sending data, tuning to this frequency range and sending data, tuning to this frequency range and sending data, tuning to this frequency range and sending data. By the looks of things, it takes 1, 2, 3, 4, 5, 6, 7, 8, 9 9 separate spectrum captures to build up the spectrum the spectrogram that we're seeing now. On the flip side, what's cool is we see that like all of these radio stations are like totally coming right through. I count 1, 2, probably 3, 4, 5, 6, 7, 8, 9. I don't think so. I don't know how frequently the radio stations are actually spaced. I guess it's 0.3 megahertz. So there are probably like all of these lower peaks are probably actually just weaker radio stations, but very clear that there are a bunch going on here. And this is effectively what we can do with our near field probe on our own board. So let's switch this frequency regime from that to, we'll go 30 megahertz to 100 megahertz. That's a pretty wide band and will probably take quite a while to capture. And we see indeed it does. Like we're 1, 2, 3, we're getting a very low frame rate here. And in fact, we see that we've got all of that radio station noise going on up here. One thing you'll also see is there's a dip in between each thing. That's because the spectrum captured by the SDR actually falls off towards the edges of the real-time bandwidth, and we can see that in the spectrogram with these like darker lines. So even beyond this, what we actually want to do is add a crop. I'm going to go with 20%, which basically just overlaps the adjacent spectrum chunks by 20% and cuts them off next to each other to try to level that out at the expense of taking longer to capture spectrum. But that sure looks a lot flatter, doesn't it? So these are pretty good settings. This is what we'll go with. And let's hook up the bigger loop near field probe that I was using earlier. And hang out over this board and see what pops up. Ooh, we got a lot going on here, don't we? I sure see a nice, bright, big, happy peak around 50 megahertz. Interestingly, I see another peak right below it. I'm going to go ahead and call that 48 megahertz. We got a whole lot of stuff going on up above 70 megahertz, but frankly, I'm just going to ignore that for now. Let's see about zooming in on that area. And obviously the disadvantage of doing this, and this is where your cost constraint is a trade-off between features and convenience and money. Because this updates like one chunk every couple of seconds, like this tells us what's going on everywhere in the spectrum, but not everywhere in the board. If I wave my wand around to like whatever section of the spectrum it happened to be sampling in that time, we'll get caught. So like we've got this thing, I'm gonna click it and then take my sample away. And we're gonna see like weird sections of the spectrum have changed and not all uniformly. But anyway, what we do now is, okay, we see those peaks. We see like 48 and 50 megahertz as definitely peaks. So let's narrow our gaze a little bit and search just between 45 and 55 megahertz. That's still more than, oh, my keyboard is again not working. 45 and 55 megahertz. That's still more than the real-time bandwidth of our SDR, so it's not going to happen instantly. But, oh boy, that certainly happens a whole lot faster. If we take our probe and wave it over, and this is another one of those situations where we've got a lot of peaks going on here, and if I simply unplug the Lana, that's interesting. All of those disappear and the noise floor drops precipitously. So we are actually measuring some artifact of either RF interference that's going on in the room right now, which is entirely plausible, or yeah, I think we're actually measuring real RF, because if I unplug our antenna completely from the low noise amplifier, the noise floor drops as well as all of those individual spikes. So what we're seeing on the spectrogram here is real. Who knows where it's coming from? I'm not going to try to find out for now. What we definitely see is there is a colossal 48 megahertz peak there, and there is a colossal 50 megahertz peak there. So, and as we move it around, we see different things happening. So this is definitely what we're kind of looking for. And what I really like about Q Spectrum Analyzer is at this point we can just narrow in a little bit further. Let's go with 49.5. Oh, Let's go 49.5 and 50.5. So that's definitely within one spectrum. And as soon as if we successfully start it, I don't know, maybe I have to tune one full spectrum, 49 and 51. Huh. I guess I can't tune that narrow. It doesn't like it. And at this point, I would probably reduce my bin size too. But this is now going nice and fast that I can wave my magic wand around the board and figure out, oh yeah, it's definitely worse up here. And there's something going on down in this bottom right corner, but it's definitely worse the closer I get to the LED. And you can do all of this in QSpectrum Analyzer. And you can also add some nice features if your VM is up to the task, which I've definitely had mixed success with. But we can add some level of persistence. I'm going to drop the bin size to 1 kilohertz just to make it a little bit prettier. We can add some persistence where now we're starting to get a little bit of that digital phosphor effect. A little bit poor man's compared to SDR Angel. So if you're in one span, you might as well want to switch over. Oh, it looks like the noise floor is actually coming from my ESD mat. That's cool. And this is one of those areas where it might be better to have a properly shielded probe. Maybe that's actually what we're picking up, but obviously this is still useful even given that. Anyway, I like doing this kind of work kind of stuck in QSpectrum Analyzer because it's flexible enough to do swept bandwidth and multiple captures in sweep mode, or like zoom in for effectively real-time analysis on one real-time bandwidth segment, that sort of thing. I hope I've given you enough to play around while I've just been talking for like the last half an hour and like actually have a decent time sniffing around signals on your own boards. But I do want to show you one last thing to maybe whet your appetite. If you have to do this seriously, I would probably recommend getting a hack RF rather. This hack RF has one massive, colossal, excellent feature as far as QSpectrum Analyzer is concerned, which is it has a swept measurement mode. So where QSpectrum Analyzer and RTL Power, FFCW, and all these libraries backends basically capture one section of spectrum, move to the next section, capture, move to the next section, capture, and so on and so forth. QSpectrum HackRF has a HackRF sweep support where it behaves completely like a swept spectrum analyzer. That obviously has its disadvantages, but the sweep rate on this thing is super fast. So let's see what that actually looks like. I am going to stop. Unfortunately, I'm going to unplug my tiny FPGA because I need the USB port. So I'm just going to demo this on the Alpha board. But let's connect you to Dragon OS. I'm going to go to Settings, HackRF Sweep. I am going to leave all of the other settings default. And let's do this same spectrum that we were just measuring. So we're going to go, again, there's sort of a theme here. Choosing settings that you are almost certain will work from the get-go is usually the best choice. And then you could throttle up the level of math that your computer and software is going to have to do from there. So let's go 49 megahertz and 50 megahertz, which is well within the 20 megahertz capture band, real-time bandwidth of this guy. I'm going to go with 10 kilohertz, and let's see. Okay, cool. Oh my goodness, it's capturing fast enough that I actually think I locked it up. I think I needed to set the settings interval, the interval to 0.01 again. Okay, just gonna kill QSpectrum Analyzer. we're gonna retry that. As fast as you can might have been overzealous. 0.01. We are still on HackRF Sweep. Let's go 49, 51. Oh, actually, on the board I'm going to demo, it's the 60 megahertz is the key. So we're going to go with 61 and 59. And bin size 10 kilohertz. Start. There we go. Cool. Notice that this is mind-blowingly fast. So the HackRF just has an update rate much faster than the RTL SDR in the first place, minus 100. The HackRF is faster than the RTL SDR in the first place, and also has a wider bandwidth. So it's faster from a bunch of different wait, 59 and 61. Oh, okay. Interesting point that's happened here. I'm getting the entire capture bandwidth of the HackRF1. So there wasn't any advantage to begin with, but for the sake of making the display look convenient, I'm going to actually center on the 60 megahertz. So we're going to start at 50 megahertz and go to 70 megahertz. This at least will center my 60 megahertz frequency of interest. Let's bring over the Alcatraz board. Have a sniff around. That's slightly unexpected. So I have something going on. I'm not noticing a particularly substantial increase when I actually sniff around that thing. I wonder if my setup is actually slightly too noisy for this test case or something like that. That doesn't make a ton of sense.
Hey, Alex.
Yeah.
Hey, you're not connected to the HackRF. Your coax isn't connected.
Nice. Good work.
Could see it from our view.
That'll be my. I'm capturing the E field without any amplification or receive antenna. Well, that'll explain why it doesn't matter how I move my magic wand. Nice spot. And actually, a secondary point, because the HackRF does not have a bias key built in, we're going to have to power the LNA from an external source to make it even turn on. So that makes things more interesting. It also did I click? Ooh, that's a lot better. Wow. And in fact, we can see something particularly cool here, which looks like we've got some sort of spread spectrum something going on. We see that like barber pole effect in the spectrogram in the waterfall. Something is rapidly changing its center frequency over this range. It looks like maybe that's the switching converter or something like that. We can have a look a little bit closer. Now we can definitely see that 60 megahertz peak driving up and down as I move around near the offending pin. It looks a whole lot like I'm off the charts there. Yep, and I stopped directly on top of that decoupling capacitor that I believe is just right next to the 60 megahertz output. Yeah, so that's a pretty successful test in my book. The last thing I want to show is, okay, we're within the real-time bandwidth of this device right now, so it makes sense that the update rate is pretty fast. In point of fact, I don't know if it's even capturing the full real-time bandwidth right now. I'm not sure how HackRF sweep is implemented, if it's still actually sweeping a tuning frequency or if it's just capturing one chunk and calling it a day. If I start at 30 megahertz, and jump up to 100 megahertz. So this is that entire, this is still capturing pretty dang zippy. Oh, that's my cursor at 70 megahertz, it looks like. Is it? That looks like a grid line at 70 megahertz, not actually a line. Either that or it's just a really, really narrow line. I don't actually know what's going on. That looks very odd to me. It looks like it's a stuffed cursor. Yeah, I think I would ignore that. anyway, let's plug in our big wide probe and look around. We've got basically the like RSA speed. Granted, it's just on a peak line, but over that massive bandwidth, and we can see all of those peaks. So the Hack RF is really, really good for this kind of work because it supports great sort of pseudo swept spectrum analysis features. Just for giggles, I think it actually might be the cursor. Yeah, it is the cursor. It's just so stuck that I can't do anything about it. I probably need to make the bin size a little bit bigger to make the math a little easier. Let's kill that and start again. One regular theme of, at least in my experience, SDR software is that frequently just restarting the software is actually the best and fastest strategy. So let's go from 30 megahertz all the way up to 6 gigahertz and see exactly how fast that happens. How cool is that? We're getting basically like 1 hertz update rate of the entire frequency spectrum that we are capable of measuring with this device. And what's doubly cool is we see a lot of spikes popping in. I am nearly certain those aren't our device, especially given how intermittent they are. But keep in mind that I am immediately next to a mesh network base station blasting 2.4 gigahertz frequently enough to mess up all my Bluetooth devices, and also 5 gigahertz Wi-Fi. So I'd be willing to bet that 2.4 gigahertz spike that keeps popping in is that router. I honestly don't know what that 4 and change gigahertz line we're seeing in this region is, and so on and so forth. But you can imagine that if you were in an all clean RF environment and you were just knocking around your board with a near-field probe trying to find this stuff, you will probably have a relatively easy time of it with the Hack RF and Hack RF sweep enabled. And you can do this with the RTL SDR. It's just a lot slower and less convenient. So all sorts of options. And I hope at this point you have basically just tuned me out and spent the last half an hour like fiddling around with your own boards and sniffing around for your own pleasure. But I guess we don't have a ton of time left now, but yeah, I guess any any questions or difficulties or like need help with anything before we knock out so that they can use the room again? I'm gonna try to open up the chat and see if I can follow.
I have one question.
Yeah.
I'm doing basically the same thing. I have a Siglent spectrum analyzer, but I think it's the same principle.
Yep.
Have you had any experience with building your own listen or common mode probes?
No. And that is definitely like next thing on my list as far as compliance interest. So for background, for anyone else who might not be familiar, we've been covering radiated emissions primarily. Another seriously important aspect of emissions testing is conducted emissions, especially for stuff that plugs into a wall. So the question is, what kind of noise are we blasting out over the power supply into our device, like back into the rest of the household or an office or whatever? The question is basically like, have you tried building your own cheap hardware for doing those sorts of measurements, which are among other things, require a line impedance stabilization network and some other hardware? No, I have not played around with building any of that myself. In theory, I believe the technique is completely applicable. If you build your own, listen and filter hardware and all the rest of it, you should well be able to conduct conducted emissions testing this same sort of way. And you might even be able to get away with doing that from a pre-compliance standpoint, because basically the issue that we have here is we have no idea what the power into our device actually means. Like the LNA isn't calibrated, the line losses are not calibrated, the antennas are far from calibrated. Like none of this gives us an accurate measurement. On the other hand, if you if you're building your own connected hardware and leaving like DIY antennas out of it and whatnot, you can probably characterize all of that stuff reasonably well with a nano VNA or something like that, to the point where you can get an at least calibrated, if not necessarily accurate, measurement setup. So if you're a bunch of dB down, you're 10 dB below the limit or something like that, you are pretty confident at that point it's good. No, I haven't tried it though.
Okay. Yeah, and I noticed that many of the commercial listens, they are quite expensive and they can handle a lot of amps, but I also found some online where you have a SMD board that can handle up to 10 amps and fairly high frequency. So I thought it was quite interesting.
Yeah, one thing that strikes me as true this day and age in engineering, especially with RF stuff like this, is stuff just doesn't cost that much to design anymore. Like it doesn't cost that much to build, I should say. So if you want serious gear that does a good job, that will cost you money. Like this Tech RSA, its real claim to fame is that its offset is basically negligible and very well calibrated when you move from one thing to the next thing to the next thing. Like one chunk of spectrum and whatnot, which is definitely not true of the SDR stuff, like the hack RF and the whatever. You notice that the like noise floor of the hack RF doesn't look like it drifts around as it scans, so it's like pretty good. But the RTL SDR and whatnot, the noise floor may be different, the gain may be different at different points in the frequency spectrum, and all of that is going to kill you if you're trying to make like actual pre-compliance, like calibrated pre-compliance checks. Which we avoid the need for entirely because we're just qualitatively looking for where stuff is coming from. So you probably run into that as a problem. But anyway, the real point of that statement is like you're paying for the effort that goes into making something that's flat and calibrated and predictable, not something that meets the like baseline like load requirements or that sort of thing. Like you can just get good components cheap these days and highly capable.
Alex, we appreciate it. Thank you for sharing with us that really fascinating and informative talk. It was very clear and straightforward.
Good.
Thank you for boiling it down.
I don't believe you, but thanks.
So, not at all. But I'd like to invite everyone to continue the conversation with comments and questions to the Hackaday.io's webpage in the chat room. And I posted the link onto the side in the Zoom chat room. And with that, I'd like to thank everyone here for being a part of such an amazing community and for joining us for Remoticon 2020. So I hope to see everyone else in more rooms. And again, Alex, appreciate it. Thank you for taking the time and teaching us something really awesome.
Yeah, same. Thank you guys for listening. I'll see everyone over in the Hackaday.io chat.
Awesome. All right. Thanks, everyone.